Alright, so the general power rule we had was the antiderivative of x to the n was going to be equal to, so the antiderivative of x to the n dx is we would add 1 to the exponent, divide by that new exponent, and then add your constant of integration. But we made sure that n was not equal to -1 because we didn't want to blow up the internet by dividing by 0. So we didn't have a case for how we would do this with the -1. And so we defined the integral of 1 to x of 1 over t dt. We defined that to be the natural log. And the second fundamental theorem of calculus then gave us that the derivative of the natural log was 1 over x. And so if I want to take the antiderivative of, for instance, du over u, it's equal to the natural log of absolute value of u plus your constant of integration. We need the absolute value because we don't want any domain issues. So natural log is a logarithm, so it's a positive happy creature, which means it doesn't like anything negative and anything zero to be fed. Alright, so we'll do a few examples of some antiderivatives with the exponent being -1 on our power, or on our base. So like an x to the -1 here, like the 5 x to the -1 here. So it just becomes 5 natural log absolute value of x plus the constant of integration. And then if we take the derivative of that, we should get back to the original integrand. Okay. So we'll do some stuff that's a little bit more fancy, and then sprinkle in some of the u substitution technique also. So here again, I don't see anything apparent here to do here other than maybe try u substitution. General convention is let u be the denominator, so u equals x to the 5th plus 7x. Take the derivative of that. Du is 5x to the 4th plus 7 dx. So the numerator is all taken care of by du, and the denominator is just u. So the antiderivative of 1 over u du is going to be the natural log of the absolute value of u plus your constant of integration. And then we'll just plug in what u was originally equal to, and u were originally x to the 5th plus 7x plus constant of integration. Okay, so I'm just using your integration by substitution. Okay, let's try another one. So upstairs there I have x cubed minus 1, that's a difference of cubes, so I might try to factor it and see if that goes anywhere. And the factor downstairs is an x plus 2, so I'm not going to have any like factors to divide out. So at this point in time I have two routes. I can either use long division or synthetic division to see if I can make this a little bit more manageable. Because the bottom factor is, or the denominator is linear, I'm going to use synthetic division. I'll put -2 on the outside. Coefficients go 1, 0, 0, -1. X cubed, x squared, x, and the constant. So we need a placeholder for everything so that the synthetic division works. Okay, so bring down your 1. 1 times -2 is -2. 0 plus -2 is -2. -2 times -2 is 4. 0 plus 4 is 4. And 4 times -2 is -8. -1 plus -8 is -9. Okay, so there's my remainder, my constant, my x, and my x squared. So that's what my integrand will become now after I've done that long division. So x squared minus 2x plus 4 minus the 9 over x plus 2 dx. Okay, all this stuff there, I already know how to take the derivative of. X squared will give me 1/3 x cubed. Minus 2x, the antiderivative will be -x squared. The antiderivative of 4 will be 4x. And then this new piece, the -9 over x plus 2, okay, is going to be -9 ln absolute value x plus 2. Okay. Alright, so 1/3 x cubed minus x squared plus 9, I'm sorry, plus 4, minus 9, absolute value inside a natural log of x plus 2, plus constant of integration. Okay? Alright, let's do maybe one or two more here. Maybe just one more. I think we'll do two more. Let's do the antiderivative of tan, which is something that we don't have yet. And one of our strategies for dealing with trig functions sometimes is write it in terms of sine and cosine. So write it as sine x over cosine x. And we're going to do some u substitution. We're going to let u equal the cosine x. So du will be negative sine x dx, which is the numerator off by a negative. So it'll be antiderivative of negative 1 over u du. And hey, we know what the antiderivative of 1 over u is. It's ln, absolute value of u, plus your constant of integration. So negative ln, absolute value, and u is cosine x, plus constant of integration. And if I want to use my properties of logarithms, I put this negative 1 back up. So I'd have cosine to the negative 1, which is the secant. Then the ln absolute value of the secant of x plus c. So either of those is good. So now you have the antiderivative of tan. And we'll do one of the other ones. So if you can do the antiderivative of tan, then you could figure out cotan. Cotan's real similar. We'll look at antiderivative of cosecant, and that's real similar to derivative of secant. So if you can do the cosecant, then the trick for the cosecant is real similar for the secant. Okay. And so I don't see anything obvious. I mean, I can write it as 1 over sine, but then, okay, well, I let u equal sine, then du is cosine dx, and it doesn't really help me. So we're going to do a fancy trick here, and we're going to multiply cosecant x by a fancy flavor of 1 here. So we're going to multiply it by cosecant x plus cotan x all over cosecant x cotan x. So remember, the cosecant and the cotan kind of go together, just like tan and secant go together. And we'll go ahead and multiply the numerator out. So we have cosecant squared x plus cotan x. I'm sorry, plus cosecant cotan x, and then the denominator is cosecant x plus cotan x. And now I'm going to try to do u substitution. So we'll let u equal the denominator. And this is looking good. So du will equal negative cosecant x cotan x minus cosecant squared dx. So I got the numerator there just off by a negative sign. That's all right. We can handle that. If it's off by a constant, that's fine. All right. So then it's equal to negative 1 over u du, and I know what that is. It's negative ln absolute value of u, but u is cosecant x plus cotan x plus your constant of integration. If you want, you can put that negative sign in there and fuss with all the stuff inside there. You'd have to combine like the fractions there, and you can go a little bit further than that. Okay. So I would encourage you to try to do the same thing for finding the antiderivative of cotan. It'll be a lot like this: find the antiderivative of tan, and then try to find the antiderivative of secant. It'll be a lot like cosecant. Instead, you would be multiplying by secant x plus tan x, and it's very similar.